Welcome everyone to our webinar on Python 2 Advanced Algebraic Modeling using Gurobi and Python. A little background information. This is the second in our series on optimization modeling in Python. Now, we were going to focus on Python today. However, you can build optimization models in other popular programming languages. This series is focused on special features for Python that are helpful and useful for building optimization models. Now, since this is an advanced presentation, we assume you are familiar with Python and with optimization modeling. However, if this is new to you, please check the resource section on www.gurobi.com and particularly view the recorded presentation, the first in this series, Python 1, Introduction to Modeling with Python. So our agenda for today's webinar is got three parts. First, we're going to get started using a simple example from workforce scheduling. This will introduce you to some of the concepts in optimization modeling in Python. Then we're going to talk about general concepts in optimization modeling. And finally, we're going to translate those general concepts to Python and the Gurobi interface and see how the general modeling principles can be applied using Python and using the Gurobi interface in Python. So let's get started with a simple example of workforce scheduling. So here's a model called workforce, and we're going to solve a classic model to assign workers to shifts. Now this model is infeasible, so we'll do some tests at the end to determine why it's infeasible. We're going to start with the data. And there are two types of list data in this model. First, there are shifts, and second, there are workers. So we have a list of shifts, which is 2 weeks. This is a simple model where there's one shift per day, and so we have 2 weeks. Monday, the 1st of the month, Tuesday, the 2nd of the month, Wednesday, the 3rd of the month, and going on through the first week and repeating itself for Monday, the 8th, Tuesday, the 9th for the second week. So 14 shifts, and we have 7 workers, Amy, Bob, Kathy, Dan, Ed, Fred, and Gu, A through G. Those are simple lists. And then we have index data. Now these data are indexed by those two lists before. First, we have shift requirements, which are indexed by the list of shifts, and that's how many workers are required for each shift. So for example, on Monday the 1st, we require 3 workers to work. On the second day, Tuesday the 2nd, we require 2 workers, and so forth. We also have index data for worker pay. That's how much we pay each of these workers. So that list of workers is used to index the worker pay. So Amy is paid 10, Bob is paid 12, Kathy is paid 10, etc. Let me go ahead and read that first list of data and read the list of index data into my optimization model. This is an interactive system that I'm using for this demonstration. Now we have something that's a bit more complicated. We have the list of worker availability, and this is the list of shifts when workers are available. So on any particular day or shift here, the worker may or may not be available. The way we're going to represent that is using a list of tuples or of pairs, and this makes the model much more efficient. We're only going to list the shifts that are possible because we can't or we don't want to optimize for shifts and workers who are unavailable. So let's look at some of these examples here. Amy is available on Tuesday the 2nd. However, she is not available on Monday the 1st, nor is she available on Thursday the 4th. So we have an entry for Tuesday the 2nd, Amy for Wednesday the 3rd, and then we skip to Amy on Friday the 5th. And we also skip Saturday, and we go again at Amy Sunday the 7th. So there are some shifts when Amy is available, others when she is unavailable. We're going to list the ones when Amy is available, save for the other workers, Bob, Kathy, Dan, and so forth. Let's read that in. And now we have the data complete, so we could represent the decision variables in our optimization model. We're going to use the variable x WS is equal to 1 if worker W is assigned to shift S. Again, we're going to use that list of availabilities, which represents only the possible combinations. We're not listing every combination of worker and every combination of shift. We're going to use that special list we just saw that represents when workers are available, and we're only going to have a decision variable X for the possible combinations. This reduces the model size and makes our code much more efficient. Now, our objective is to minimize the total salary cost. And we're going to, that's going to be the sum of the combination of pay and XWS for each WS and availability. So if XWS is 1, we're going to pay the worker for that shift. And if not, then we're not. And we're going to minimize that objective cost. And now our constraints. We've got a shift requirements constraint that says for each S in shifts, the sum of X for each worker must equal that shift requirements. So it's going to sum up of only of the workers that are available. So this is very efficient. It only matches the workers that are available for a particular shift. Now, this syntax is a little funny. So I've got in the comments just below another version of this where I could write it out explicitly in terms of that availability set. So I could say, this is an alternate syntax. It would do the same thing. That if I said for each S in shifts, I could add the constraint with the sum of XWS for W in workers if the pair WS is in the availability. That would do the same thing, but this would be less efficient than the version I have just above it. So we'll talk more about efficiency in just a moment. Now we're going to solve the model. And remember, at the beginning, I said that this model is designed to be infeasible. So I'll optimize the model, and you see in the output, this model is infeasible. This is just a simple example. So what do we want to do if it's infeasible? We've got a few techniques, and since this is the full Python interface, the full Gurobi solver is behind it, we could call the fees_relax function to relax the constraints, find a solution that's nearly feasible. So I'll solve this model, and here is a minimum relaxation of this model, and we find there are 4 shifts that need to be relaxed. On Thursday the 4th and Saturday the 6th, we need to relax the constraints by 2 units, meaning we're going to have 2 fewer workers than requested. And on Sunday the 7th and Friday the 12th, we're going to relax the constraints by 1 unit. We're going to have 1 worker fewer than the request. And again, since Python's a full programming language, we could do all sorts of interesting stuff at the end. For example, I could show a little plot that displays the shifts that couldn't be met. So if you see here, the darker shaded rectangles represent the shifts where there was a shortfall, and the most dark ones have the shortfall of 2. The medium dark ones have a shortfall of 1. And that's a nice little plot that shows our output. So let's go to general optimization model principles. Well, the first and most important part of an optimization model is the decisions. What are you going to do in an optimization model? These are the optimization variables. And in our workforce example, we had a simple decision. Do we assign a worker to a shift? So we had that list of workers and a list of shifts, and we had that special list, which was the combination. We decided whether or not that worker was going to work the shift. But in general, we've got lots of different kinds of decisions in optimization models. We'd be trying to select something or assign some equipment or some people to something. If it's a manufacturing model, we might have some make decisions. Do we make something? How much to make? Go, which would be if it's a transportation model, and also buy or sell. Do we want to buy or sell products, equipment, whatnot? And these types of decisions could be yes/no decisions, or they could also be quantities. How much are we going to do? How much are we going to build? How much are we going to buy? Now, there are also quantities in optimization models, and these are numerical values that are used in relationships. They become the coefficients in expressions, linear expressions, quadratic expressions, logical expressions, any kind of expressions in our optimization model. In our workforce example, we used cost for a worker in a shift. We also had the quantities, the number of workers that were requested for each shift. But there's other quantities as well beyond the workforce model. We could have cost, we could have price, we could have distance, how far is something, space, how much space does something take. We have the time that something requires, the materials required or used, which you might see in a manufacturing application, supply or demand if you're buying or selling something, or if you have raw materials, and capacity, which might involve workers or equipment or raw materials. Now, the constraints in an optimization model are the requirements or limits. These are equality or inequality relationships. In our workforce example, we needed to assign enough workers to meet the requirements for each shift. So we have other optimization models might involve demand that has to be satisfied. We might have equipment that has limits. We have supplies, we may have limited supply. We might have space limitations in a layout. We'd have limits on the number of workers or the availability of those workers. We could have money. We might have a budget limit that we have to meet. We also have time. We might have a limited amount of time to do something. These are just some examples. And then the objective is our goal to achieve. This is the mathematical function that we're trying to optimize. In our workforce example, we were trying to minimize the labor cost. But when that model was infeasible, we solved a second model with a different objective where we added slack and surplus values, variables to the model, and we wanted to minimize the shortfall in the shifts. In other optimization models, we might try to maximize profit or maximize the utilization or balance. We could have used balance in the workforce example. We might have wanted to make a schedule that used the workers as evenly as possible so that the schedule was balanced. We could also have minimization objectives. We might want to minimize cost or minimize the time to do something or minimize waste used in a manufacturing process. Finally, optimization models involve indexes. These specify a key value. They identify an element of an array. In our workforce example, we had three types of indexes. We had the workers, like Amy and Bob. We had the shifts. In our workforce example, they were days. But in a more complicated workforce example, we could have had shifts within days. And then availability in our workforce example was a list that specifies a shift when a worker is available. So it was a combination of a worker and a shift. There are other kinds of indexes for other types of optimization models, including products that we might be manufacturing or requiring. We have workers. We might have equipment that might be required, machines or trucks. We have locations that might be places we could travel to or places we might be manufacturing products. We could have customers or suppliers. We also have individual supplies that might be required or used. And time is a common index, and even within time, there's different ways of representing it, different levels of granularity. You might have a fine-grained model with minutes or hours. You could go to days or weeks, and then you can get into larger or longer-term models with months, quarters, or years. So these indexes are key to optimization models. They describe the individual variables. They also describe numerical quantities, and they describe the constraints. Indexes can be used in a couple of different ways. They're used to iterate over variables or constraints. That's like a mathematical for all statement. They're also used to compute sums over variables and numerical quantities. Now, when you're building an optimization model, to make that model efficient, it depends on proper handling of these indexes. For an efficient model, the setup should require much less time and memory than solving. And the examples I'm showing today are written to be efficient models. It's possible to write some models that are inefficient. I'm not going to show that style. I'm going to show the style of writing some efficient models, models that will scale well as your data sets get larger. That workforce example and the example I'll show near the end are very small examples, but they have the style that if I had a much larger data set, they'd still solve very efficiently. And although I'm using Python, the idea is that the setup time, the time to build the optimization model, will be much less than the time it takes for the Gurobi algorithms to compute the optimal solution to these models. So let's talk about some general principles in Python programming and the Gurobi interface. But before I get to the Gurobi interface, I need to talk about some general ideas from Python. So first, we're going to talk about Python lists, and we saw these in the workforce example. In Python, a list is a built-in data type that can store other items. They can store integer-valued items, they can store floating point values, they can store strings, they can store tuples, which are pairs of items, and we saw that in the workforce example where the pair was a combination of a worker and a shift. They can also store other objects. Now in Python, a list is ordered, meaning the order is preserved. When we had that list of shifts, Monday came before Tuesday. Python lists efficiently support iteration and random access, and Python lists can be modified. You can add things into a list, like an append operation. You can also delete things from a list, and you can join or concatenate multiple lists together. Lists are a very good way to create optimization indexes. They are a little different than a mathematical set because lists can contain repeated elements, but they're a very efficient way to build these indexes. There do exist other data types in Python. There exists a set that doesn't contain repeated elements. That's generally a little bit less efficient than a list, but it's there if you need it. Now there's a special feature in Python called list comprehension. If you're not a Python expert, but you have some experience in optimization, you're familiar with the idea of set builder notation. And this is really the same idea in list comprehension. So let's take a look at some simple examples. I could build a list of squares using another iterator. So here I'm going to iterate through a range, which I've got 6 elements. And in Python, when you use a range, it generally starts from 0, though there are ways to call the range function and start from 1 or start from another value. But here we're going to count out 6 elements, 0, 1, 2, 3, 4, 5, and we want to create a list of the squares. So our list is created by I to the second power for I in the range of 6, and this will create the list 0, 1, 4, 9, 16, and 25. So those values are squares. We can also use multiple iterators, and here we've got a list of tuples, ij. Now, it doesn't matter, I've got the choice if I can iterate on I first, or here I'm going to iterate on j first. So I'm going to iterate for j in range 4, which is going to go 0, 1, 2, 3, 4 on j. And here's something interesting. For I'm not going to iterate on a fixed value, but I will iterate on a value that depends on j. So for I in the range of j, so what does that look like? When j is 0, I has no range. There's no range 0 to 0. That's empty. When j is 1, I'm going to iterate from I in range of 1, which is the value 0. That gives me the pairs 0, 1. When j is 2, I will iterate on the range 2, which gives me the values 0 and 1. That gives me the pairs 0, 2, and 1, 2. Same thing when j equals 3, I will be the range of 3, which is 0, 1, 2. That gives me 6 values, those 6 pairs in the line afterwards. I could also use a filter, which is an if condition. So I could create a list called the non-squares for I, of just simply values I, for I in the range 10, meaning 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. However, I add the condition if I is not in that list of squares I had at the beginning. So that gives me the list. It doesn't include 0 or 1 because those are in the list of squares. It gives me 2 and 3. However, 4 is skipped because that's in the list of squares. 5, 6, 7, 8 are included, and 9 is skipped because 9 is in my list of squares. Now, list comprehension syntax is similar to optimization notation, as I said earlier, And anything you do in list comprehension syntax, you could do in standard programming using for loops, but that tends to be a lot more wordy. For an example, think about that pairs list that I created earlier using the list comprehension syntax. I could create that using two different for loops. I say for j in range 4, for I in range j, and then I say pairs.append the pair ij, and I have to add another line at the very beginning to create an empty list so that I can append these values into this. So this is equivalent to the line earlier where I used the list comprehension syntax, but it takes 4 lines. And frankly, I like the first version because it looks more mathematical and it's more compact. It's very easy to read, but they're both equivalent. You could use either one. They'll both work just fine. Python has another feature called generator expressions. Now, you might not remember all these funny names, but the idea of generator expression is very similar to list comprehension. It just omits the intermediate list. So remember when we had that list of squares on the previous slide, I wanted the list of 0, 1, 4, 9, 16, and 25. Now that creates a list, which is some extra storage to save that list of 6 squares. If I wanted to just compute out the sum of those squares, I could skip the extra storage and the extra step of computing that list by using a generator expression. It has the same syntax, I to the second power for I in the range 6, but in the second one, I omit the extra pair of brackets inside, and that way it doesn't compute that intermediate list. And if I don't need to store it, this is a little bit more efficient. And that will compute out that sum, which would be 55, which is the sum from 0, 1, 4, 9, 16, and 25. Now, the Gurobi interface takes advantage of lists and of the list comprehension syntax and generator expressions. And we'll show that in just a moment when we get into the Gurobi syntax. But before that, I'm going to talk about two special data structures that Gurobi introduced with the Gurobi interface. The first one is something we call a tuple list. Now, this is like a list, but it's designed to store tuples specifically. Suppose I have a list of cities, A, B, C, and D, and then I have a list of routes. Now, those are pairs or tuples, but it's not every combination of cities. It's just this list of 5 of them, A to B, A to C, B to C, B to D, and C to D. So it's not every combination of 16 pairs of cities. It's just this subset of 5. Now, what if I wanted to iterate over this list of routes somehow? Let's say I wanted to look over each city and I wanted to find the list of routes that leaves from that city. So we have a special function in the Gurobi tuple list called the select statement, and this gives efficient filtering. So if we iterate for each C in cities, so for the first one, when the C equals A, we would print out the list with routes.select starting from A, and that gives us the list A, B, A, C. Now that notation says we're going to start from the value C, which equals A, and then the star means give me all the matching values that starts with the first value. So that gives us the list A, B, and A, C. When the city equals B, it gives us the list of routes that start from B, that's B, C, and B, D. When the city equals C, we have the list just simply C, D. And in the last case, where the starting city is D, there are no routes that start from D, so therefore it returns the empty list. And what's very nice about the Gurobi tuple list class is that it's indexed to make this select statement very efficient. So what that means is that the first time we compute out this select statement, we compute it out once, and then the subsequent ones use this index, and that makes it very efficient. This iteration becomes very, very nice. There's a second class called a tupledict, and this is like a tuple list, but it's a dictionary class where the keys are tuples. The list of keys, in fact, is a tuple list, so you've got the select, sum, and product operators on the tupledict. This is used throughout the Gurobi interface when you create decision variables and constraints, and I've got some examples in my next couple of slides. So, In the Gurobi interface, we've got two functions that allow us to create variables and constraints in bulk, and those are returned as tuple-dicts. So the first one, the one you're going to use the most, is going to be Model.addVars, which has a bunch of different ways you can create variables. You could use integers. In this example, I'm going to call m.addVars 2, 3. So that's going to give me variables that are indexed by two different values. The first one's going to be the range of 2, meaning 0, 1. And the second index is going to be a range of 3, meaning 0, 1, 2. And so this gives me 6 variables, x00, x01, x02, and x10, x11, and x12. So a very nice way to create 6 variables in just one statement in Python. Now, a more interesting one would be to use other lists. So we can call it using lists of scalars. So here I go back to that list of cities I had a few moments ago, which were cities A, B, C, D. And this time I'm going to create the product of two different cities. So this gives me 16 variables. These will be variables called Y. And so now I've got the variables YAA, YAB, YAC, YAD, etc. So I've got 16 variables. But I could also create variables indexed by the tuple list. Remember, in my tuple list, I had a list of routes that wasn't every pair of cities, it was a subset of them. And we saw this in the workforce example. Here I've got a list of 5 routes, and so now I've got 5 variables only indexed by that list of routes. So here's my list, my variables now ZAB, ZAC, ZBC, ZBD, and C indexed by CD. I could also use any kind of Python iterable, including a generator expression. I don't think this is something you would do often, but this just shows you the power of the Python programming language and the Gurobi interface. Here I could create variables that meet some kind of an expression. Here I'm going to say for all I in a range except for the value 2. So I've got variables W0, W1, and I skip when I equals 2. And then I've got W3 and W4. This probably isn't something you're going to do very often, but it just shows you that this is a very powerful thing, these generator expressions with the Python interface for Gurobi. So this Model.addVars function will automatically take the cross product of multiple indexes. We saw that in our prior slide. We used integers, so that gave us 6 variables indexed by 2 different values. When we used integers, we also did that using the list of cities, and we just repeated the cities to create the variable Y. We also had that Z variable that was indexed by the sparse list of routes, but when we created Y, we used all combinations of cities. In addition, the Model.addVars generates names automatically using the subscripts. Now, there is one important limitation to the addVars function. It requires lists of scalars or lists of tuples. It doesn't work with arbitrary lists in Python. But those are very common things you use in optimization models. There's a corresponding function for adding constraints to your optimization model, and this is called the addConstraints function. This uses a generator expression. If I have variables indexed by routes, so I've got X and Y, these are 2 different variables, and let's say I've got a capacity constraint, then I could say that m.addConstraint, so I'm going to add the capacity constraint xij plus yij is less or equal to 2 for each ij pair in routes. And my generator expression is this thing that says for all ij in routes, and I'm actually creating a constraint for each of those pairs. And this is very nice. It's very algebraic. It does exactly what I might write if I were trying to write a mathematical representation of my optimization model, but it allows me to do that completely within the Python programming language. Now, there's different kinds of operators you use mathematically, and they have corresponding functions in Python. When you're building linear and quadratic expressions, such as in the constraints and the objective, there's a bunch of different mathematical operators you have. You have basic or binary mathematical operators. By binary, I mean that they use 2 different terms, your plus, minus, multiply, and divide operators. Those exist in Python. And also there's something called the aggregate sum operator, We often represent that in writing it using the sigma symbol. And you could use this alone, but you could also use it in products or dot products. I'll show some examples of that in a few moments. Now, when you're using this aggregate sum operator, the indexes are very important to using it. The Gurobi Python interface has two different versions, a full version and a simple version. Why are there two? Well, the simple version is much easier to write, it's shorter, it looks a little cleaner, but there are some things you just can't do with the simple syntax, and so you could use the full one, which isn't that much more difficult, and it allows you to do some things more general. So let's take a look at some examples of this. The aggregate sum operator in the full version, we use a generator expression inside of a quick sum function. So we might want to represent the objective for our model of the quick sum of the cost ij times xij for each ij in arcs. So that's a nice mathematical function, and we use something called the quick sum function. Now, the quick sum function is a special feature in the Gurobi Python interface. It's really the same as Python's own sum function. However, it was built for the purposes of optimization and is a bit more efficient. It's not a huge difference, but it's a nice small improvement in performance for the setup of optimization models. Now, it won't change anything in terms of the solving time, but it is a little bit more efficient for the building of an optimization model. Now, what about the simple function? We have a function called the sum function when you're using a tupledict of variables. So this is a special feature that we've added to the tupledict, and it uses the same syntax as tuplelist select. So again, let's say I have a list of variables, a dictionary of variables x, which I've created using the addVars function 3, 4, meaning we're going to have two different indexes, and these are going to be binary variables. And then I might want the constraint x dot sum of I, sum where I comma star, meaning for a particular I want all of the j values less than or equal to 1 for I in the range of 3. So this will generate three different constraints. It generates a constraint when I equals 0 of x00 plus x01 plus x02 plus x03, meaning it's finding all the matching j's when I is 0, and it adds the constraint those x's are less than or equal to 1, and it does the same thing for I equals 1 and I equals 2. And so this is very nice because I didn't need to use a generator expression for the sum. I just used this sum function, which magically computes out the different matching x's for when I is a specified value. There's a corresponding value or function, for the dot product, and a tupledict of variables also has this prod function that computes the dot product. So, for example, if cost is a dictionary, then the two things below are equivalent. I could use the quick sum function and compute the objective of cost ij times xij using the generator expression for all ij in arcs. And that's the same thing as saying x dot prod of cost, and that computes the dot product. Now, if cost was not indexed by ij pairs, it was only indexed by I, then I can't use my dot product because that would have a different index. Then I would just simply use the quick sum function in the first line using the generator expression for ij and arcs. But in this example, cost has the same dimensions as x, so I can use that nice dot product function. So let's take all of these concepts we've seen and use them for a second example. Let's look at a network flow example, a bit more complicated than our first example. Let's solve a multi-commodity flow model in Python using Gurobi Optimizer. Again, we've got this list data that we talked about a moment ago, and now we've got three different kinds of lists. We've got our commodities or products that we're going to manufacture, our nodes in our network, and arcs in our network. And our arcs are tuples that represent not every combination of nodes, but a subset that represent the arcs in our graph. So our commodities are pencils and pens. Our nodes are cities, 6 cities in the US, Detroit, Denver, Boston, 5 cities, Detroit, Denver, Boston, New York, and Seattle. And our arcs are 6 arcs that are representing different combinations of cities from Detroit to Boston, Detroit to New York, Detroit to Seattle. Now we have index data. We have our capacity, which are indexed by arcs. So our capacity has a capacity on each arc, Detroit to Boston, Detroit to New York, Detroit to Seattle, etc. So those have capacities of 100, 80, and 120. For costs, this gets a little more interesting. They're indexed by the combination of commodities and arcs. So not only do we have the six arcs, but now we also have multiplying that by the two commodities for 12 different cost values. The cost of transporting pencils from Detroit to Boston is 10. The cost to transport pens from Detroit to Boston is 20. We also have our inflow, which is the amount of flow at each node of the network, and that's also indexed by a combination. This time it's a combination of the commodity and the nodes. So we've got 5 nodes and 2 commodities, so that we have 10 different inflow values. So the inflow, the value of or the availability of pencils in the node Detroit is 50, but the availability of pens in the same node of Detroit is 60. So let's read that data into our optimization model. So now we've done the data, we can now start creating the model itself. We're going to use that function Model.addVars to add the decision variables, and the addVars can take 2 different arguments. Here we're going to have a combination of every commodity and every arc. And so we're going to call this flow values. It's going to have an objective. We're going to create the objective at the time we're going to create the variables, and that's going to be the cost values. And so we could just do this in one step. This will create that list of that tuple dict of flow variables. Next, we can create the constraints in our optimization model. We'll use the Model.addConstrs function. We're going to call it twice using several different Python generator expressions. We've got constraints for arc capacities and constraints for flow conservation. We've got a generator expression that's going to create an arc capacity for every arc ij. We've got a generator expression that's going to create the flow for each commodity and each node j. And then inside of each constraint, we're going to use the aggregate operator tuplelist.sum to compute the sum only over the matching elements. Again, this is a beautiful thing because it's not going to look at every combination of cities. It's only going to find those for which there's a flow variable, meaning for which there's an arc in our network graph. So our first one, we had the flow capacity on each arc for ij and arcs, and we're going to take the sum over all the commodities. So that we say flow.sum, we use the star because the first index is our commodities. So star comma ij, and that's less than or equal to the capacity. In our second constraint, we have the flow conservation, which says that for the flow into node j, so for each commodity h and for each node j, my flow into node j, so I say flow.sum h comma star, meaning all the arcs that flow into node j, plus that additional inflow value, that's that data, h comma j, must equal to the outflow, the flow out of that node j. So I have flow.sum parentheses h for the commodity h, and the flow out, so there we're going to use j as the first index, and then star means all of the values that match for that third element of that tuple. And now we'll solve and print the flows. So I'll optimize my model. This is a very simple model, but it has the structure you might find in other kinds of network flow optimization models. And here's our solution, which is printed out in plain text. Now I'm also going to, for debugging purposes, I'm going to write the model out as an LP file. So that's going to create a file called netflow, which I'll look at in just a moment. But before I do that, let's take a look at the output. So since we're in the Python programming language, we can show the output in lots of different ways. Here I'm going to show a chart, a bar chart showing me the flow on each arc. And I use colors to represent the different commodities. So red represents pencils and green represents pens. So on Denver to Boston, I have a flow just of pens. From Denver to New York, I have a flow just of pencils, but on the arc Denver to Seattle, I have a combination of pencils and pens on that arc. In addition, I can use another library to print out my results in a table format. Now, a moment ago, I also said something about debugging. I wrote out a file called netflow.lp, which I can use for debugging purposes, and here I'll open it up. And so here's our model written out in long form, in an algebraic form, but without the nice expressions that we had in Python. But I can look at this to see, is this the correct representation of my model? So for example, I look at lines 11 and 12, and I see that the capacity constraint on my arc from Detroit to Boston is equal to the flow of pencils plus the flow of pens on that arc Detroit to Boston, and that must be less than or equal to 100. I could check my data and make sure that's correct for representing the capacity on that arc. And for flow conservation, let's look at lines 23 and 24. The flow conservation at the node Detroit is equal to the flow of the arcs out of Detroit, Detroit to Boston, Detroit to New York, Detroit to Seattle, and that only involves pencils. And that's because that's the flow conservation of pencils at Detroit, and that equals minus 50. And I could just see the same thing for other combination of nodes and commodities in my network flow graph. So this is just a little introduction to building algebraic models in Python. We have a lot more examples on the Gurobi website. If you look at this link, we have two kinds of code examples that are very helpful for this type of algebraic modeling. We have functional code examples. They tend to be a little smaller, but they show the different Python and Gurobi functions for building optimization models. We also have more mathematical examples called modeling examples. And these examples come from this book called Model Building in Mathematical Programming. If you're fairly new to optimization modeling, this is a very good book for getting started, because this book covers a lot of different types of optimization models and different domains in mining and manufacturing and transportation, and covers the full mathematical logic in building that. And so on the Gurobi website, we have a number of the examples from that textbook written out using the Gurobi Python interface. Another way to learn about the Gurobi Python interface is the Gurobi Python documentation. And the Gurobi documentation is found in two different parts. The quick start guide is really to get started, but the full syntax of the Gurobi interface is in the reference manual, and there's a special section of it just on the Python interface. And if you're still learning Python, I think the best resource for Python is python.org, www.python.org. And there they have not just a reference manual, but a very good tutorial for learning about the Python programming language, as well as ways to download Python, how to install it, how to run it on different systems. It's a fantastic resource. There are other websites for Python, but this is my favorite. So at this point, I'm done with my prepared presentation.
Thank you very much, Greg, for this very interesting presentation. We have received quite a few questions, so let's get started. Is it possible to input costs and parameters from spreadsheets, text files, and so on, like we do in AMPL? If so, how?
Great, absolutely. The answer is definitely yes, because Python's a full programming language, and it has tons and tons of libraries for data manipulation. I didn't show that in today's webinar because I wanted to show some simple examples. But in fact, in the Gurobi distribution, we have an example that solves the simple diet model that all of us have seen in school. And what's nice about the diet example, first of all, it's a simple model that all of us understand. We've all seen it before. But the second thing is that in our example in the Gurobi libraries, we show this diet example in a bunch of different ways. One that just reads data from a hard-coded data from within Python. Second, that reads it from separate Python files. But then, more to your question, we also show that you can use that same format to read data and to write the solutions to spreadsheets, to relational databases, to simple databases like SQLite. And that's the beauty of Python. Python's a very modular programming language that supports tons and tons of databases. And there's built-in ways to do that using the libraries that are included with Python. There's also some very advanced libraries for Python data manipulation. I briefly showed one in the network flow example, which is called pandas, that allowed me to write this nice little table that you're seeing at the bottom of my screen. But that pandas library also includes some very powerful ways to manipulate data to and from external data sources, including from the R programming language, a very popular language used for data representation. So when you download and install Gurobi on your computer, look to the examples/Python subdirectory, and in there you'll find the diet examples, and those diet examples will show you. There's a bunch of different versions, and they'll show you exactly the syntax, one syntax that you can use for reading and writing data to and from spreadsheets and to and from external databases. So yes, absolutely it can be done. I just didn't show it in this presentation today because I wanted to keep things simple, but we have examples that are included with Gurobi. Great question.
Thank you. Then I have a more general question about efficiency. Is a list with tuples generally more efficient than using a dictionary?
So the two are not mutually exclusive. They're actually very complementary. I don't think one is particularly more or less efficient. In fact, in our Python examples here, we use both. So let's look at the network flow example, although we did the same thing in our workforce example. We had lists of commodities and nodes. Now, those were simple lists. We also had this list of tuples of the arcs. So those were just lists, but we used dictionaries that were indexed by these lists when we used the capacity, the cost, and the inflow. So those are dictionaries indexed by combinations. And then here, the Python interface for Gurobi, when we called the M.addVars function, that returns out dictionaries. And here that's a dictionary of flow. So we use that dictionary of flow, which represents our optimization decision variables, and that's indexed by lists. So the two are not mutually exclusive. They really, I think, go together hand in hand. So we have the list here of commodities and this sparse tuple list of arcs, and we create the combination of that, and that creates a dictionary, and that dictionary is indexed by a tuple list. And that's what's really nice about the Gurobi Python interface. We provide these two special classes, the tuple list and the tuple dict, and in fact the key values from our tuple dict is itself a tuple list. Just like in the base Python libraries, a dictionary's keys is itself a list. So the two go together all the time. I don't think one is really particularly more efficient. They really are they go together.
Thank you. Then there is one question about that constraint in the very bottom. In the second model, you used variable.sum in your constraint. Does this work with quicksum?
Absolutely. So everything I did here, I used that simple form because it just makes the code nicer and simpler. In fact, let's just do that so I can show you, make things just to show you, yes, I could get the very same model. Let's do cap equals M.addConstrs. I'll just do it for the first one. For simplicity, I'll use quicksum flow Hij for H in commodities. Hope I spelled this correctly. Less or equal to capacity Ij for Ij in arcs. And I need to put a parenthesis around this. I almost made that mistake. I'll call this capacity. And let's hope that I did everything correctly. So let's run it from the start, read our data, create our variables, create our constraints. Yes, no syntax error. And let's see, the prior solution was 5.5, so let's re-optimize and hopefully, yay, it works, 5.5. So these are equivalent. Yes, we could definitely do everything using the two different forms. Here, I just rewrote that first one using a quick sum, and that quick sum for each H in commodities, and that works. Now, for the second one, it would be a little bit more complicated because I'm trying to find the matching ones, but it certainly could be done. It's perfectly fine. I prefer the simple version when it's, I like to keep things simple when possible. But yes, you could definitely use a quick sum. And there are, as I said earlier in the presentation, there are some times when you can't use this simpler form. And so you could certainly use the full form to use a sum or quick sum. So the two are equivalent. I just have a preference for the simpler form when it's usable. Great question. Thank you.
So back to the Gurobi solver. Is it possible to get the current best solution while the algorithm is still running?
Absolutely. So there's a couple of different ways to do that. The Gurobi Python interface is a full interface to Gurobi. And this is, earlier that question was, why would you want to use the Gurobi Python interface instead of some generic interface like Pyomo? This is a good case where you would want to do that. If you want to use that solution, maybe you want to print it out or write it to a database as it's being solved and not just wait for the end. You could do that with a callback function. So callback functions are functions that get called within the optimization, and they allow you to do your own code inside of the optimization, including Python code. It doesn't have to be complicated C or C++ code. You can write Python code that does anything, including retrieving these intermediate solutions. So that you do using a callback function. And we have an example of callback functions in Python. Again, and the example is Python subdirectory when you install Gurobi on your computer. There's a simpler version. If you don't need them at the time you're solving, you just need them at the end. There is a way to pull the intermediate solutions from the Python interface using our attribute interface. But that only lets you get the solutions at the end. It doesn't let you get those solutions as they're being generated. Now, these examples I use today are very simple. They solve quickly, so there's really no real benefit to having to go through the extra coding of writing a callback function. But in more interesting optimization models that take much longer to solve, that could take minutes or hours to solve, then there's some benefit to getting those intermediate solutions and either displaying them on the screen or writing them to a file or a database. And that you could certainly do through callback functions.
You mentioned that when a set of constraints is infeasible, you could relax them. Is this relaxation like passing from hard constraints to soft constraints? And could you elaborate more in the types of constraints available?
Sure. So Gurobi has a couple of different methods for dealing with infeasible models. And by the way, these features are not specific to Python. They're available to all the Gurobi interfaces. One is the IIS function, which computes what constraints are conflicting in a model. And the second is fees_relax, which is just a convenience function, does something that many of you have done yourselves. It adds slack and surplus variables to the model. Now, I called it, in the workforce example, I called it using the most simple syntax, but you can control it and tell the solver what you want to relax. Here I called it just using a simple version where I told it I want to relax all the constraints. I don't want to relax variables, because you could relax variable bounds, but here I just wanted to relax constraints. I want to relax all the constraints. You could control it and say, just relax these constraints, and it's just a nice convenience function for adding the slack and surplus variables. What I didn't show, but you can also do, is you can call fees_relax in a couple of different ways. Here I just wanted to find the minimum relaxation. You could also call it in a way that says, first relax the model, and then take that as a constraint and go back and optimize the original objective, but with that particular level of relaxation. And you could do that as well. And there's a lot more examples of that in the Gurobi documentation. Of course, you could always do this yourself by adding slack and surplus variables to your model. But the fees_relax function is a convenient way of doing that in a very simple way using one call, the Gurobi interface.
And one last question. How does Python performance compare with Java or C++?
Great question. So Python is a little slower than other languages because it's interpreted. Now, Java is sort of interpreted and sort of compiled. Python's also sort of compiled. It's a little bit like Java, but without the separate compilation step. The compilation is done on the fly with Python. But both Python and Java are really interpreted languages. They have an intermediate interpreter. C++ and C, of course, are pure compiled languages. They are creating object code, compiled code, machine code on your computer. So they are going to be a little bit more efficient. But the real question to ask yourself is, where is the bottleneck in your optimization application? In the vast majority of optimization applications, a very small amount, if the application is written correctly, a very small amount of processing time is spent building the optimization model. A lot of it is spent sometimes in data processing, but in many applications, the real bottleneck is the actual computation of the optimization solution. And that's going to be the same no matter what Gurobi interface you're using, because the Gurobi solver is natively compiled. So whether you're using C, C++, Java, .NET, Python, R, MATLAB, whatever Gurobi interface you're using, the computation is going to be the same. And in most applications, that computation is 80 or 90%. It's whatever is the overwhelming majority of the computation time. And so the setup time for a properly written Python application, I do want to emphasize properly written, one that's efficient, that uses the data structures that I've talked about today very efficiently, that's going to take a relatively small amount of time. And so, sure, you could reduce that if you use a compiled language like C++, but if you're going to take the total solve time and look, if the total solve time is 15 minutes and 1 minute is spent in setup time, is it really beneficial to reduce that 1 minute down to 30 seconds when 14 minutes might be spent in the optimization algorithms? And so in those cases, you're probably better off looking at performance tuning for the Gurobi optimization algorithms, perhaps using a larger computer, looking at different parameters that are going to make that run faster. Now, it is true, there are some applications for which you need to reduce the setup time. If data processing is the bottleneck, you can still use Python, but then you might want to use a specialized system for data processing like Pandas, where the data processing is very efficient within Python. So it'd be faster because that's going to go on in compiled data, in a compiled library like Pandas, rather than an interpreted like Python's built-in data structures for lists and dictionaries, and Gurobi's interfaces for tuple lists and tuple dicts. You could use the Pandas library. So the first step should be to figure out what's the bottleneck. If your bottleneck is data processing in a database, that's not going to change if you're using C++ or you're using Python, because your database, be it Microsoft SQL Server, or if it's MySQL, that's going to be the bottleneck in setup time, not the Gurobi Python interface. Or if it's manipulating files on your computer, the input and output on your disk might be the bottleneck, in which case, hey, looking like a solid-state drive might speed things up, and Python isn't really the bottleneck. But there do exist a small set of applications. I'd say it's maybe 5% of Gurobi applications for which setup time is a significant amount of the solve time, and those do benefit from using a compiled language. But they're very small, relatively small number of applications. Most applications can be very efficiently written in Python if you write the Python correctly, as I've shown, using the data structures and using a proper sparse data representation in Python. You can write inefficient code or efficient code in any language. If you write your code efficiently in Python, it's going to run very efficiently, and it should be, in most cases, a relatively small part of the setup time. If you've got specific concerns about Python performance and you're a commercial customer, contact Gurobi support. We'll be happy to work with you. We'll be happy to point you to some of the profiling tools to help you decide whether or not the Python overhead is a significant amount of time, help you with looking at logs and looking at your total application time to see whether or not Python setup is or any kind of model setup, even in other programming languages, is a significant amount of the total solve time, and help you with different ways to reduce that.
Thank you, Dr. Glockner.